everyone, in this video I'll be looking at z-scores and the standard normal distribution. I'm going to assume that you're already at least a little bit familiar with the normal distribution. I will link the normal distribution introductory video in the description. I have here on the screen the formula for the normal distribution curve and a picture of some sample normal distributions. In general, our normal distribution is a continuous probability distribution that has a peak right at the mean, and then the spread of the bell curve line is dependent upon the standard deviation or the variance. So we can have different types of normal distributions depending upon the mean and the variance values. The standard normal distribution, however, is the specific normal distribution where the mean is 0 and the standard deviation is 1. So we get a peak right at 0 and the spread is sort of set at that standard deviation. If we have values from any normal distribution, we can standardize that data or that random variable into the standard normal distribution by using a z-score. So we just take our data value or our variable value, which is typically represented by an x. We do x minus mu, meaning x minus the mean from our normal distribution or for the population, and divide that difference by the standard deviation. And we get what's called a z-score. So here's an example. Women have heights that are normally distributed with a mean of 65 inches and a standard deviation of 3 inches. So that gives us a random variable that is normal, but it doesn't follow the standard normal distribution since the mean and standard deviation are not 0 and 1. What's the probability of randomly selecting a woman who's less than 5 feet or 60 inches tall? So we can take that 5 foot or 60 inches value and standardize it within this population by turning it into a z-score. So we're going to do this calculation here. I want my x value, which in this case would be the 60 inches, my mean, 65, and the standard deviation, 3. Here's what that looks like. So 60 minus 65, that would be a negative 5. This is negative because 5 feet or 60 inches is lower than the mean. And then divided by 3, this gives me about negative 1.67. So when you calculate z-scores, the way you want to think about them is it's measuring how far away from the mean this data value is in terms of a number of standard deviations. So this is between 1 and 2 standard deviations below the mean. That's what a 60-inch tall woman would represent. In the standard normal distribution, negative 1.67 falls to the left of the peak. It's a negative value, so it's below the mean of 0. And it's a fair amount below, but not really far into the tail. Negative 1.67 is sort of a low z-score, but not unusual or unlikely z-score. In terms of the question that was asked, what's the probability of randomly selecting a woman who's less than 5 feet tall? If we turn that 60 inches height into a z-score, then this is looking at the standard normal distribution and the z-score of negative 1.67 and saying what is the area underneath our normal distribution to the left. That area is representing a probability or a proportion of the total, and that would be the probability of getting a woman less than 60 inches tall. If we're doing this with z-scores, we can look up that area using a z-score table. I'm showing here the z-score table that's in our online textbook. There are lots of these z-score tables online and in various different statistics textbooks. You probably have one available wherever you're learning about statistics. But in this table, you'll see some z-scores listed down the left-hand side with additional decimal points going horizontally. The numbers in the center of the table represent the areas. So I need to look up the z-score negative 1.67. So I need to go to the negative z-score values And I'm going to go to negative 1.6, and then I need to go to the column that gives us a 0.07. So I'm going to scooch back up here. The column 0.07 is right here, so I'm going to scroll down. So negative 1.67 takes me to this box right here. This is showing a number 0.0630. So that is the area to the left of the z-score, negative 1.67. So that little area shaded to the left of the negative z-score in my picture corresponds to 0.0630. If you're using z-score tables, this is how we compute probabilities like this question. If you're using technology, you can compute this directly without using a z-score, but this is just an alternate method. So this means that the probability of randomly selecting a woman who's less than 5 feet tall is about 6%, or 0.063. Here's another example question. So within this same population of women, what's the probability of selecting a woman who's between 5'2" and 5'9"? So if I want to do this using z-scores, I need to calculate the z-score for each of these heights. I'm first going to put these in terms of inches. 5'2" is 62 inches. 5'9" is 69 inches. And so I'm going to calculate our z-score for the lower height. This would be 62 minus the mean, which was 65, divided by the standard deviation, which was 3. And those values are just coming from earlier in the example. For 69 inches, I have 69 minus 65 divided by 3. You can calculate these in a calculator or Excel or whatever method you're looking at. If you do calculate these in something like Excel or a graphing calculator, make sure that you're doing the subtraction first before the division. So if you enter it all as one calculation, you need parentheses around those subtractions. 62 minus 65 is actually just -3. So this is a z-score of exactly -1, meaning that someone who's 5'2" is 1 standard deviation below the mean. And for the higher value, this is 4 divided by 3, or typically we're going to write z-scores as decimals rounded to 2 decimal places. This is 1.3 repeating. I'll just round it to 1.33. So the probability of getting a woman in between these two heights would be equivalent to the area between the z-scores -1, which is somewhere to the left of center, and 1.33. I'm just roughly placing these in a bell curve picture to give me a visual sense of what we're trying to find here. We're trying to find the area in between those two z-scores on the standard normal distribution, or under the standard normal distribution. Now, if I go back to my z-score table, I can look up the z-score -1 and the z-score 1.33, but the values it's going to give me are just the area to the left for each one of those points. So we have to adapt this and say, okay, if I find the area to the left of -1, and then separately I find the area to the left of 1.33, I can find the area in between them by just subtracting the two. So I'm going to look in my z-score table. I'm in the -1, so -1.00 would be this first entry in the -1.0 row. That's 0.1587. Just going to write that one down and then go to my z-score table, to the positive z-score table, and find 1.33. Here's 1.30123 would be this value right here, 0.9082. So this is telling me that the area left of 1.33 is 0.9082, area left of -1 is 0.1587, and I can just subtract these, subtract the smaller area from the larger area, and get my area in between the two. So I get 0.7495. Now in the context of this problem, this means that about 75% of women are between 5'2" and 5'9", where the probability of randomly selecting a woman in this range is 0.7495. The last example showed how we can use z-scores to find the areas underneath the standard normal curve. We can also use z-scores just directly as a way to show where a particular data value falls among a population. So in this example here, I have two different students, Emma and Liam, and Emma scored 1350 on the SAT and Liam scored 28 on the ACT. And I want to know, how can we compare those two values? I can't directly compare SAT and ACT scores because they're from different score ranges. So who performed better? I need to compare Emma's score relative to all the scores in the SAT and Liam's score relative to all the scores in the ACT. And I can do this with z-scores. So I'm going to compute Emma's z-score. That would be her SAT score, 1350. And then I want to subtract from that the mean SAT score and then divide by the standard deviation. This example lists that SAT scores are normally distributed with mean 1029 and standard deviation 235. So I'd have 1350 minus 1029 and standard deviation. So we're dividing by 235 for this z-score. These figures are coming from the 2025 SAT, and I got them from collegeboard.org. You can do this calculation on a calculator. I did mine in Excel, so I just did this 1350 minus 1029 in parentheses divided by 235, and I got Emma's z-score to be 1.365957. The convention here is typically to round z-scores to 2 decimal places, so I'll round this to 1.37. And Liam's z-score, I'm going to do the same thing with our SAT population. So his score was 28 minus, I need the mean score on the SAT, which is 19.2, and divided by the standard deviation from the SAT scores, and that was 5.8. These numbers are from 2023 through 2025, and I got them from act.org. So again, calculating this on a calculator or in Excel, I get 28 minus 19.2, all divided by 5.8. This gives me a z-score of 1.52. Now I could use these z-scores in the z-score table to find out, for example, what percentage of people scored better than Emma or less than Emma. But in this case, I just want to compare these two z-scores. So both of these z-scores are positive, meaning that both Emma and Liam scored above the mean, which we could see pretty easily with the scores themselves. But it's showing that Emma scored about 1.37 times the standard deviation above the mean, and Liam scored 1.52 times above the mean. So really their scores are pretty close relative to the general population, but Liam's score is a little bit better. So his ACT score is going to be a little bit more competitive, all other things equal, than Emma's SAT score. And z-scores can be really helpful in this way to compare values that are coming from different related but different valued populations. That is it for this video. Thank you for watching.